Hey, I'm Slade,
I'm Sean.
Irregular Design Group, and today we want to talk about some of the design features and the reasons why the HESYCHIA SIXK-H is the way it is, and what some of our objectives were in the design process. And if you guys don't know, Sean, my partner here, he's the head of design and manufacturing in Irregular Design Group. So, Sean, take it away.
Yeah. So the first objective we wanted to have was make sure that the can is safe and healthy to shoot. So Slade's experience, my experience with high back pressure cans in the military, I mean, I would actually like to push that story over to you, talking about like why the health is so important for us.
Okay, so a little background on
Yeah.
that. In my old command, we would train constantly. I mean, thousands of rounds a week, multiple kill house runs in a week as well, between range and assault training. We started to see a lot of health issues with guys that I worked with. And, you know, we had weird like respiratory tract tumors and cancers happening. We had weird brain cancers. And obviously we can't do a direct correlation. It's the suppressor's fault. Obviously, there's tons of toxic exposure, especially over a longer career in austere environments. But a lot of the anecdotal evidence is pointing to the toxic exposure we encounter through training, whether it be through firearms training, explosives training, and then obviously overseas you're encountering burn pits and all those other things. But it seemed to be really localized and focused at the last group I was at. And I do think that is a lot of the intense training that we go through, and a lot of that is firearms in enclosed space. And then, I mean, the cans that we shot on the 416D, like you would come out of the kill house and like the whole half of your face would be covered in carbon and vaporized CLP. Like if you didn't wear iPro, like you were crazy. Obviously we did, but like your whole face would just be covered in this carbon and CLP buildup. And if you're thinking about, well, if it's in my face, I'm obviously breathing those things in because I'm not on a breath hold for, you know, a 20-minute house run. So, yeah, shooter and operator safety became a big focus on, well, it became an awareness thing that we had when I was at the command. And obviously now that I have the opportunity to work with brilliant people like Sean, it's like, hey, we really need to focus on operator safety when we're designing this can.
So what we wanted to do is design a can that maximizes flow rate and reduces back pressure. Now there's a couple different ways that you can do that. You can vent a lot of the gas from your blast chamber straight to the atmosphere, or you could try and figure out different ways of creating different pockets and channels for the gas to be able to move through as least restricted as possible while still trying to maximize sound suppression. So for like the first 50 something prototypes, we were venting the gas from the blast chamber to the atmosphere, and it was such a pleasure to shoot. It was soft, it was quiet at the ear, but it was insanely loud at the muzzle, and we were also getting a ton of flash. So we were trying so much on doing restrictions in different areas. We were trying to change the front cap geometry. We were trying everything. And then Slade and I were just like, this isn't working, we have to change it up. And so what we wanted to do was, can we vent the gas back in at a specific point in the can? And hopefully that would give us the same low back pressure feeling of shooting without creating a very saturated pressure field coming out of the front of the can. So for the next 20 revisions, we were messing around with where we were bringing the gas back in. And then we realized that our first prototypes, you know, we had like an insane amount of geometry dedicated just to flash suppression. And we realized that if you wanted to get flash suppression, you can do it in a way that's not just with a 3-prong or like a bird cage or anything like that. We found that if we spin the gas incredibly violently, it works. And so while we were figuring out the way to vent the gas back in, we got a little clever on how we were making sure that the gas wasn't just unrestricted flowing through the can. Anytime that we had an opportunity just to change its vector a little bit, we did. And go figure, when we did that first batch of 9, we're all looking at each other like, how on earth did we get this thing that low back pressure? And we had no holes in the front of the can. And so that's when we were like, okay, I think we're onto something. And then we started messing around with another batch of down selects where, well, how much can really release through the front of the can and still be able to maintain a respectable tonality and decibel reduction without causing too much back pressure.
Also flash, right? So
yeah,
if we had too many of these overpressure events in the front, we were getting a lot of flash.
Yeah.
So we played with a bunch of different combinations of how many can we get, how many, where's that perfect where's that magic number to where we're okay with the sound at the muzzle
Yeah.
and with the back pressure and with the reduction in flash.
Right. I mean, the first ones we did were like, I'm just going to poke a bunch of holes in the front. And it was like,
Literally, like we literally drilled holes in the front.
Yeah.
To just to test it out.
and it was just like a jet of flames coming out.
It was like a cone of jets of flames with a main flame coming through.
If we would have shot the gun like this, the gun would have been a rocket. Like, but what was weird is when we were developing. So we make everything in Cincinnati, Ohio. Here we're on the West Coast, and apparently y'all's air is combustible because I would be shooting cans in Ohio, getting after it. No flames, no nothing. Everything's great. I'm like, Slade, you're going to love this thing. He gets it, takes one shot, 6-foot flame, and he's like, damn it. We put so much.
I call him immediately. Like this, everybody knows at this point, this is my little range here at my house. And I would call him from down here, send him a video, be like, bro, this is not working. And he's like, what is happening? Your air is flammable.
Exactly.
Your environment sucks. I'm like, yeah, but it needs to work in pretty much every environment. Like that's the goal is we want this thing to be, I throw it on, I don't have to tune the gun, I can just go shoot it anywhere, and I'm going to have a pleasurable experience. It's going to be safe for me and bystanders, and it's not going to throw 6-foot flames, the gas back in my face.
And then there's another time when we tested, and we had grabbed some other cans, and we're comparing, and like, we're just testing our can over and over and over again. We're like, man, this is getting better, 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 better. And then we compared it against other cans, and then he calls me back. He's like, this ain't it, Chief. And I'm like, oh. And like, I got real sad. And I call him, I was like, dude, this is okay. Now we have a baseline. And then we changed, 5 things on the next prototype. So we did a huge swing. We're going smaller.
We did a huge design revision. Yep. We did like a 6-hour video chat.
Yeah.
Did a massive design overhaul. And then from that, those principles of that design overhaul, we designed 10 variations of that can to print and test 10 variations with minor changes in between to get to our down select.
Yeah.
And then from that down select, we printed 10 more based on the best performer out of that. And that's where we arrived with this.
Yeah. Yeah. Majority, like 75% of the development of the HESYCHIA was going in the wrong direction, but we knocked out 60 something prototypes in 3 months. I mean, it was insane. Like the schedule was Monday, design for like Monday, Tuesday, we would design like 9 to 10 suppressors, start printing, slice, start printing. It takes a couple days to get that done. And then when we get the printer, the cans out, the threading, the facing, all that stuff, we go straight to the range. We actually, shout out Cincinnati SWAT. Y'all were the best, allowing us to just drive down, use your range, and allow us to use our own ammo. And we full auto mag dumps, everything, trying to figure out every different way that we can stress these cans to figure out what the best performer was. V26. V26 of the new architecture. We shot that. You were there with us.
Yeah.
And it was like...
That's where the down select really started going in the positive direction to get us to this point. And also to note, like we did the majority of testing on like 10.5 duty weapons. Like we wanted to hammer these things, induce as much stress and pressure into them, and have them perform at like the worst case scenario, which is like a 10.5 duty rifle. Like we wanted it to be the worst conditions for our testing. So and that's what we went with. We weren't trying to like create the perfect environment. We wanted the worst conditions because through that, it's like, hey, if this thing performs with crappy ammo, extreme pressure,
no tuning
whatsoever. Like this thing is meant to be thrown on a gun. Like I said, no tuning. I only have fixed gas port guns. I mean, I do have a SIG Spear LT, but I mean, that doesn't really count. I don't really use that thing anyways. But all the testing was done on fixed gas port, a DoD contract upper that I had from Noveski. And, that thing obviously has some provenance attached to it as well. So, I mean, it was a cool testing process. He had a Mark 18 out there. I had the Navy equivalent of that. Yep. And, it got us to where we are with this thing.
That was hard because when I had just got out of the Marine Corps in 23. I had no rifles. The rifle that I was testing on was a Welcome to Ohio rifle. It was just a 14.5 from our friend John Miller. And I was doing all my testing on that. So, Say was like, hey, can you grab a Mark 18 to test on? I'm like, yeah, I can ask my buddy. Shout out Brian Collins. And then we were just, the disparity between the 10.3 and the 14.5 was like, okay, we need to get one. And so, we got that. And then we had a bunch of lefties, Nick Gobley and Chris Rossiter, our resident lefties. They were instrumental in making sure that they have a lot of experience shooting. And if they didn't like it, then we can't really claim that it's low back pressure. So, a lot of times when you look at weapons, the indicator of back pressure isn't exactly in the extraction pattern. There is an intangible of open up your eyes really wide, shoot full auto. If your eyes get watery, it's too gassy.
Yeah.
And you can't really tell that from videos. So, they were shooting a Mark 18 with V26 full auto, eyes wide open. They're like, dude, this is it. And then the tonality was there. The flash was there. Compared to where we started, I mean, it's hard to get 0 flash out of a tiny little can because this thing's only adding about 3 5/8 of an inch to the end of the gun. Even in that little space, we crammed 8 baffles in there. And each baffle we designed different. So it's not like design a baffle, pattern it down a tube, ship it out. Each one was very custom. And what we would do to figure out how we would modulate our geometries for each down select is we would sit there with the Google Sheet. We'd have all the different variables that we wanted to adjust. We're like, all right, baffle density, angle, gap. And then we would say, all right, V 1, 2, 3, 4, 5, all the way up to 9 or 10. And then we would, before we start even modeling, we'd say, we're going to do this.
We would predict an outcome.
Yeah, we would have a little hypothesis column. So we would write out our hypothesis. And then we would go shoot. And we were like, hey, did the hypothesis of what we did for this configuration come true? Yes, no. And then we would write our evaluation on it, which is, I think that's called science. But
science,
yeah,
actually.
Exactly.
We were trusting the science of the scientific method, right?
Yeah.
Because science matters.
Yeah, exactly. So we did that. And as we kept working through each of the iterations, it started becoming where our hypotheses were just wildly wrong. And then the more we did this, it got to the point where V26, we were like, we believe our gut was telling us that V26 of that batch of geometry was going to be the winner. And then go figure, we shot V26 and it was the winner.
And it wasn't confirmation bias.
No.
We had other people there testing, shooting. We, obviously the Larson has shortcomings, but
yeah,
it was a way for us to pull a little bit of data, right?
Yeah.
And it was like, hey, is what we're experiencing matching something that can give us a visible metric, right?
Yeah.
We didn't have money to spend $35,000 on testing equipment.
Yep.
We didn't have money to send it out to go get it third-party tested. So
yeah,
we were doing a lot of internal testing, and we just went for it. And it was like, is our experience matching up to what our predictions were, our hypothesis, and it was as close as we'd come. And it was just like that eureka moment.
Yeah.
Right? And it was like, okay, that's it. Now let's iterate off of this.
Yep.
And from that was the last iteration of 10 based on that one. And then we got to the down select.
Yep.
And our final can.
Yeah, V26 was it. And then we just made a little adjustments. We thickened some areas up. We added a little bit more texture because I model everything on Fusion 360. And it doesn't use your GPU. It's all off your processor. And this can was breaking my damn computer with the texture pattern and everything that was going on.
Internal geometry.
Yep.
Yeah.
So we did a lot of our down selecting without some of the more subtle features of texturing and adding different features that would just give it subtle adjustments.
Some of the anechoic features internal that ended up in the final were not in the down select, but we knew that those things would add capability and performance.
Yeah, because we started to figure out oh, this is kind of what's going on in there. We didn't use computational fluid dynamics. We didn't do finite element analysis. We didn't do any of that stuff.
We did use flow bench testing though.
The flow bench, yeah. I was talking about more of the digital, the digital validations, because those you can't model turbulence very well, and you can model one shot, but what does 2 shots look like? What does 3 shots with residual pressure? The compute that it would take, and even then, I'm not an engineer, so I'll look at it and be like, ooh, colors, and then what does it tell me? it was just better for us. The reason why we bought our capital equipment and our printers is because you can lock as much of your emphasis into trying to chase specs and data and values. But at the end of the day, we started off, we wanted a healthy shooting can. We wanted to be pleasant, and we wanted to do it in a unique way. And we achieved all that. And when we got to that point, we're like, all right, this is great. Let's go down to Thunder Beast, you know? And then we're like, how do we validate there? How do we validate with other units? How do we grab as many cans as we can and go out and demo with other shooters and not just pull empirical data, but the shooter's experience? Because a lot of times when you're trying to buy something online, you only have data to make your decision off of.
Obviously, there was no scientific method in some of the comparison testing we did. I tried to be as honest as I could possibly through the experience of shooting those different cans. And I didn't say that our can is the best, you should buy it. I would argue that our can is the most pleasurable to shoot. But what is your objective? If my objective is to be the quietest at the muzzle as possible,
that ain't it.
That's not it. But there are going to be trade-offs. If we wanted a higher flow rate of a can with lower back pressure, the trade-off is it's going to be a little bit louder at the muzzle than if I had a hyper-restrictive traditional style of can. But what that does for you as the shooter when we have that higher flow rate is it reduces that at-ear decibel level. So we've got a very low weighted decibel level at the ear.
For its size.
Especially for its size. But we'll be able to share some of that data here shortly once TBAC concludes.
Yep.
And we were super pleased. It's like, okay, this data point is measuring up to our anecdotal experience and every other shooter that we've shot with's experience, right? They're like, man, what is up with this thing? It's super quiet. Well, it's super quiet from your perspective of you shooting. There's no black pressure. It's like the recoil delete button too, right? It's like the cheat code for recoil delete. It was taming down, again, like those 10-5 duty weapons that like to climb when you're shooting them. It was just straight linear recoil, right? And it just makes it super manageable.
And we got a lot of that because of the way that we did our muzzle device. So I know we don't talk much about it, but the muzzle device, we knew had to be something not just as a standalone unit, it had to be considered part of the assembly of the suppressor.
Yeah, it's a total system.
Yep.
It's not an afterthought.
Yep. You know, when people are like, oh, I need the maximal flash suppression, and they want it out of their flash hider. Okay, well, if you have a suppressor and the suppressor manages flash better than even flash hiders, if that's your concern, don't take your can off, right? I can't think of a lot of scenarios where I had my suppressor on and then I need to take my suppressor off and then take a shot where I still want to be concealed visually. Like, it just doesn't make sense. And so what we wanted to do is design a hybrid flash hider where we still get some decent flash hiding performance, but also have something that works like a brake, but not like what do they call those things? The brakes that just go out the side.
Those are called baffles.
Yeah. Oh, yeah. Funny.
Yeah.
Those things, work incredibly well for deleting recoil, but they also punish anyone to your left and the right. But it also creates hot spots in the can because you're not equally distributing the gas where you want it. So when we did this diamond pattern, we wanted to say was the first interaction that gas coming out of the barrel has with the blast chamber. Where do I want the gas to go, right? And we wanted it to go...
It's a circumferential release.
Yep, exactly. And we wanted it as even as possible, and we wanted it kind of at a vector, which goes right to where we start to dump our gas into the annulars. So if you take the sum total surface area of all the vertical features in the diamond, it actually creates a really big... It has the same amount of surface area as a muzzle brake. So this is an untimed flash hider that only uses a 3/4 inch socket wrench to put on there, so you don't need to time it. But this thing on its own, the recoil reduction is insane. And it doesn't put out this punishing blast to the left and the right. Like if you were to shoot this thing unsuppressed in a shoot house, the 2 or the 3 man isn't going to get smoked by this thing. And which was like kind of like a happy little accident. When I modeled this, like, you know, we like to put diamonds anywhere we can. And so I just did this thing, and I didn't really think it was going to work because you did the post of our little wall of shame of all our muzzle devices.
Yeah, I mean, I think we had 15 to 20 different variations of muzzle devices before we even arrived at this guy.
Yeah.
And we had variations on this. It was just like variations on a theme, like
Yeah.
over and over and
Yeah.
over again.
Yeah. Well, I did like, I think this is 5 starts. Yeah. 5 pattern instances. I tried one at 6. This thing did great on flash. 6-foot flame. Like, what? Like it was ridiculous. And then we messed around with different apertures and different internal textures. We had some muzzle devices where I was like, I'm so confident this thing's going to work. Let's print a whole batch of 18. And then I shoot it once and I just put the gun down. I'm like, this is the dumbest thing I ever designed. It was just like a 5.56, like shooting like a 308. And I was like, how did that happen? A recoil increaser.
Yeah.
It was stupid.
Flash booster.
Yeah, flash booster. It was, yeah, exact opposite of what we wanted. And so when we landed on this, we didn't apply the scientific process to the muzzle devices as much as with the suppressors.
Yeah.
In hindsight, we should have. Like these things, to get a good flash hider or to get a good muzzle brake or to design the right geometry to work for what you want in a suppressor, like it is just as important. And I know some suppressors out there behave very differently with different muzzle brakes and muzzle or muzzle devices.
I mean, that's your first incidence of gas is coming through that muzzle device into the can anyways. And that's, again, that's why, as of right now, we have no plans to do hub cans because one of the things that we built into the can, Sean, right? Remember from the very get-go, I was like, we need a secondary, tertiary locking system.
Yeah.
Just to ensure that under heavy firing schedules, these things won't start to walk off. Like, how many different muzzle devices have we seen where cans come loose, walk, and then they become part of the projectile system themselves?
Yep.
So, Sean, when we talk about the Hesian bow system, we have to talk about the intentional design behind it, right? So on the muzzle device itself, we've got the 32 ridges, 6 locking pawls. And again, it took us a minute to get to that intentional design. We started with like 49 teeth and 7 pawls, but we settled on 32 and 6. Yep. And I want you to explain the reason behind that.
Yeah. So this is it's a part detent design, but it's also a bidirectional ratchet. So typical ratchets, it's a single pawl and a bunch of little teeth. And as you're tightening something on and the ratchet's moving in one direction, the pawl will kind of bang across the teeth, but the pawl has an inverse relationship between the teeth and the pawl so that it completely arrests counter rotation, so that you have to break the pawl in order for it to rotate the other direction.
Or unlock it, right? Like a mechanical reversal,
right? Yeah. You either break it or you have some sort of mechanism that releases it. That has too much complexity. And so we were like, okay, can we just do a force to overcome system? And can we get it to where the teeth, no matter what position they are on the ridges of the muzzle device, are always going to apply some sort of force into the retaining ring. Whereas a ratchet, if I'm going to tighten something down and then the taper locks, the ratchet engages on average anywhere between like 7 to 14 degrees. Every time you hear that click, that is a range that the pawl is having to work and completely lock. But you can't tighten up something to where the taper perfectly locks and then the pawl perfectly locks at the same time. Because of that negative relationship, the pawl has to move over the tooth and then settle into the lockup, which means you don't actually have a taper lock. A taper lock, when you hit taper lock, you're there. So how can we design a ratcheting system that isn't a ratchet, but also ensure that no matter what point of rotation you're at, when that taper is sealed with the right amount of torque, the pawls are doing their job. They don't have to be in a specific position. So our system with the 32 teeth and the 6 pawls means every sub degree of rotation, we have one pawl that is perfectly settled in one of the grooves of the retaining ring. Then we have 3 pawls that are on the trailing face of a ridge. We have 2 pawls that are on the leading edge of a face. So it means at any point of rotation, if we're like right here, and I try to feel any kind of backlash, there's none. I go here, it doesn't matter, there's no backlash. I go back a little, here, it's settled right there. That was about like that 1 degree of rotation, and now we're settled. So now we have way more indexable features to guarantee that the taper is actually doing the work. It's not the pawls that are holding the system together. So the 32 and the 6 allowed us to, for one, I mean, you can achieve that same ratio of like 1 engaged, 2 in the front, 3 in the back with different numbers. But we wanted to reduce the amount of pawls and we want to reduce the amount of teeth and also reduce the amount of rotation required so that our first system, we had what, 6 or 7 rotations for it to get locked.
Yeah, it was way too much.
It's way too much. And then that means those pawls are riding across those ridges 4 times, 3 times more than what we're at here. And what we also wanted to do was make sure that the geometry of the pawls aren't sharp, because sharp things like to wear themselves out. So we designed everything to have gradual radiuses. So it's like a little, radius here riding in and out of a radiused feature. So they glide on each other more rather than hearing that like super tactile clicking of a ratchet. That is what you're hearing, is it's those 6 independent pawls just kind of sitting there feathering the muzzle device. And we've been able to test this thing. We don't recommend it by any means, but part of our validation is we've shot this thing full auto with the taper not sealed. The pawls, because there's 6 of them and each pawl puts about 8 to 10 pounds of pressure, we've got 60 pounds of force holding that can onto the to that retaining ring of the muzzle device. If we've accidentally taken the muzzle device, ran it all the way in, and where all the balls are engaged, like you can't get the muzzle device out. Like these pawls apply an insane amount of pressure to the muzzle device, but also the mechanical advantage we have from the American buttress thread allows that really low input torque requirement to overcome that system. So when you're putting it on and off, you're like, oh, that doesn't feel like it's actually locking. Well, it's just because we have a lot of mechanical advantage. And so we've been able to calculate that at 15 pounds of just hand tightening torque onto the 15-degree taper using the 8-pitch American buttress threads, putting about 1,700 pounds of force on that taper. And we're able to achieve that amount of force on the taper, not just because of the thread itself, but because we shallowed out the taper of the muzzle device so that the mechanical advantage of our input allows us to be able to convert more torque to the faces. If you run a shallower taper, when you try to input it to get a taper lock, you need a ton more force to get those faces to actually mechanically mate. So shallowing it out was a risk, because what was one of the problems that muzzle devices have with suppressors?
Well, I mean, you get them on there, and if you don't get them on tight enough, they're not making that taper lock, so your can's going to walk. Or if you do get them on there tight enough, then you cannot, without mechanical advantage of using like a wrench and a breaker bar, get that thing to come loose. So your can becomes basically fused on there until you can get a big old wrench on there with a breaker bar and break that thing free.
If anyone's been following the way that we advertise the Hesian bow system is, the buttress thread. It's like, well, why do we use a buttress thread? Why are we not using Acme? Why are we not using V-Groove? And quite frankly, the story of how we came up with the buttress thread was my partner Tim and I were at March 1st Brewing Company, and we were having a drink talking about threads, and he's like, you know what? You ever heard of a buttress thread? I'm like, no, sounds hot, but you ever heard of buttress thread? And he's like, dude, this is what they use to thread tank barrels into the upper assembly of the fuselage, or whatever they call that top turret area. It's the same thing that they use for sealing artillery chambers. So when you put the shell in, you close that chamber, you do that rotation, those are all buttress threads. Well, if those are good enough for tanks and artillery to be able to manage high heat, high vibration, high pressure, why is no suppressor using this buttress thread? And so we started digging into it, started doing a ton of math, and one of the other benefits of the buttress thread is the angles that the thread is designed in. It's a 7-degree load face and a 45-degree trailing face. So that thread is designed to convert all of its torque in one direction. It's a unidirectional power transfer thread, whereas Acme is a bidirectional power transfer thread. So Acme is used in the kinematics for CNC machines. It's used as, pretty much any kind of mechanical assembly with a motor is driven by an Acme thread. The problem with Acme threads is, for this kind of application, is that it's a very tight tolerance where it's inherently a non-backlash thread. So it's designed to run incredibly tight on the front and the rear face of the thread. So if you do have slippage of carbon past your taper seal, you don't have a lot of space for that thing, or for the carbon to be able to escape. It'll build up on the threads, and then you get carbon lock.
Well, yeah.
Right?
Sucks.
And it sucks. And the thing is not every system is always going to maintain a perfect taper seal. So if the system fails, how can we guarantee it doesn't fail catastrophically? So what we did is we actually, I think the term's called truncating, and the top of the thread, the crest, We bobbed that down, or trunk, I don't know what it's called, but we actually took the crest back a little bit so that if the seal is broken for whatever reason, when gas is bypassing, because of the very gradual 45-degree leading edge of the thread, and then the excessive gap on the crest to the root of the thread major inside the suppressor, gas will just blow out the back. So if for whatever reason that seal isn't there, your system's not going to get stuck because we gave the carbon an area to escape and not deposit. And by it being Inconel, we have the thermal properties of the suppressor and the muzzle device having the same thermal coefficient of expansion. So if I have a 17.4 stainless steel muzzle device, which can grow at a different rate than the Inconel, if I have a taper lock between two different materials and one grows and one doesn't at a certain temperature, what's going to happen?
Yeah, you can have now a thermal lock.
Yep. And how many times are you mag dumping at the trash pile in your backyard? You want to take your can off at some point. It's almost impossible without adding mechanical advantage because you've yielded the muzzle device inside of that system. So by having the muzzle device not only be hollow to where the cross-sectional thickness of the taper is the exact cross-sectional thickness of the taper inside the suppressor, we guarantee that everything is going to expand and contract at the same proportional rate to where thermal locking is not going to yield inside of your can. It also allowed us to be able to use more complex geometries for the muzzle device itself. It allowed us to hollow out the system more effectively to have a pretty lightweight muzzle device for it being Inconel.
Yeah, so I think I'm scienced out.
Me too.
I've been trusting the science long enough to know that the science never lies.
I can't even spell science. So
Trust the science, bros.
Yeah.
Just trust the science. But let's go see the results of all of this science that you put into this, and the math, and the testing, and everything else. Let's go shoot these things, man. I'm bored.
Me too. Wait, a tactical montage? What? God, that trigger's fast. Oh, that trigger's fast.
Yeah, that gun's fast to shoot.
Woo!